Okay, so I know everyone's eagerly anticipating their coffee break and poster session. Like last year, what we wanted to do is have a quick opportunity for the individuals presenting posters who aren't giving lightning talks to just come up, have a brief, maximum 90 seconds. It doesn't have to be 90 seconds. They could however long they want. And introduction of who they are, what their effort is, and then just try to, I think there are about 10 folks. So we'll, no further ado, first one's Takashi Ando.
My name is Takashi Ando from IBM Research. Our poster is titled Signal and Noise Extraction from Non-Volatile Memory for Neuromorphic Computing, a machine learning-based approach. Analog memory is a key building block for the non-von Neumann computing, such as in-memory computing or deep neural network acceleration or spiky neural network. But in reality, what we have available is very non-ideal device. And here's our example of hafnium oxide-based resistive RAM. And here, device conductance as a function of input pulse is shown. And as you can see, the trace is very nonlinear and very stochastic. So, and this stochasticity is related to the inherent randomness related to the oxygen vacancy movement in the system. And this makes the evaluation of signal and noise itself very challenging. And conventional approach is to use some predetermined equation and fit the trace and extract the signal and noise. But there's no universal equation that fits for all, and that brings a lot of significant error in fitting. So instead, in this work, what we did is we established a non-parametric fitting model based on Gaussian process regression, and we extracted the signal and noise from the data itself without any physical assumption. So our approach is therefore agnostic to the device physics or types of device. And we made analog memory using hafnium oxide resistive RAM and also GST-based phase change memory. And we show that our methodology is applicable in both cases. And using this technique, we were able to extract the key parameters for the neuromorphic computing. And if you want to learn more, please stop by our poster.
Next up is Bill Aronson.
We've been talking a lot about using silicon, but in my company we've decided to play with another material. So if you get a chance to come over, I'll talk about the matrix, which is it's a first attempt to do some work, I think, in the space of analog computing from our company. And what we're focusing on is replicating the human reflex. So when a reflex happens, such as a blink, for example, there's no processing which takes place in that. It's just instantaneous. There's a stimulus and there's a response. But it probably took millions of years of training to be able to do that. But once it's done, it's instantaneous. So what we've done is we worked with a bunch of different materials, and we had a bit of a breakthrough in November of last year. We've discovered a material which will operate under normal conditions. We've attached electrodes to it. Some we've designated as inputs, some as outputs, and some as control lines. And we have proven that we can actually program this matter so that it does computation. Depending on the input signals that we use, we can either make this material behave so that every single blob of this matter is different in its response. So that opens up some really interesting opportunities for unique IDs, for security, for puff devices. And at other frequencies, we're going to get consistent response across every single one. So that then opens up the possibility of instantaneous, virtually no power, and zero processing. So if you're interested, come and catch me at some point or come over to the poster. I can show you some examples of that. But we are at the process now of having designed a circuit board. It's being manufactured over the next 2 or 3 weeks. By April, May, the latest, I think we'll be able to demonstrate and one thing we'll be able to demonstrate is a secure hardware-based reservoir computer. Thank you very much.
Next up, we have Francis Chance.
Okay, it's not alphabetical anymore. I can't. Do I have to? All right, hi, I'm Francis Chance. I'm going to be the posters about some work that I've been doing at Sandia, looking at the retina for inspiration for algorithms that can be implemented at the sensor to down-select certain types of distractor signals that might be occurring for the sensor. What the poster is about are how different models of motion-sensitive cells, ganglion cells in the retina, how they respond to different types of stimuli, for example, noisy stimuli or stimuli where there's a moving stimulus and the camera's jittering around. So this is work done with Christy Warrender, who's not here, so if you want to hear more, you have to come and talk to me, but please do visit the poster.
Thank you, Francis. Next up is Gangotri Chagma.
I'm Gangotri Chagma from University of Tennessee. My poster is on energy and area efficiency in memristive neuromorphic architectures. So from the topic you can tell, we consider in this work designing some neuromorphic architecture using emerging technologies like non-volatile and nanoscale memristors. We use to build the synapses in our design. And then we have mixed signal, integrate, and fire neurons. In this work, we consider mixed signal architecture because when we think about the system level design, we try to communicate from the external world to the chip as digital signals. But inside the core or the neuromorphic chip, we try to calculate or do all the calculation in analog domain. So that's why we try to implement it in mixed signal design or system. And then we have online training and offline training and online adaptation in the whole architecture. So as you can see on the bottom picture, that's the first layout, taped out version of our whole neuromorphic system. We have our mixed signal architecture and also our fully digital implementation in the whole chip. We have taped it out with collaboration with SUNY Polytechnic, New York, Albany. We have also done some energy analysis with some estimation for different memristive devices and how we can improve the area and energy efficiency considering different sizes of capacitances and different devices to build new memristors. So if you want to know more about this work, please find me. My poster is on 119. Thank you.
Thank you. Next up is Srijani Day.
Hello, everyone. I'm Srijani, and I'm a graduate student at Washington State University. This work was part of my master thesis while I was back at TU Berlin. So the work was to learn a fixed-length embedding of a variable-length data for the airfoils, as you can see. So the work involved exploiting the characteristics of the RNN that they are able to deal with sequential data. So as you can see that here we have a lot of airfoils. They do have a similar geometry, but they all look different. That is, they're all representing different sequences because they are made up of different points. So the idea of this work was to provide the network with a few features and not all of them, and see if the network was able to recreate that. So what we have is that with a fixed embedding dimension, with a random airfoil, as you can see here, what the network gave us was this. So the main aim of the work was to achieve a perfect reconstruction for a threshold embedding dimension without playing with the activation functions or the number of epochs, but then just the custom loss function. So what I did was the solution approach, I would say, is regulate the two aspects of the network. That is the reconstruction as well as the smoothing. And for that, I introduced a loss function with a smoothing constant. And the results that we had was there was significant reconstruction with a smoothing constant for 0.9. And we used autoencoders here, and LSTMs produce much faster convergence than the RNNs. I talked a lot about a lot of words, but if you want to know more, please visit my poster. Thank you.
So next up is Alex Dimitrov.
Hi, I'm Alex Dimitrov, Washington State University, Vancouver campus. Connect to Srijani, I'm Srijani's current advisor. On this slide, lately I've been interested in ideas of perceptual invariance in biological systems and how to achieve them. So what you're seeing here is on the right. If you think of it as a section of visual cortex, primary visual cortex, the object is moving in different positions, and of course that modulates the tuning of the neurons. On the other side, on the left, you're seeing a stage after transformations where I believe we achieved invariant processing, a model of another part of the visual cortex. It's receiving the same inputs, but it's not changing as the position of the neuron is changing. How we get to that, based on probabilities and probabilistic inference, but come to my poster, and if you're interested, we can talk about it.
Thank you, Alex. Next up is Jonas Jovenspek.
Hello, my name is Jonas Jovenspek, and I'm from IMEC in Belgium. So IMEC has a lot of expertise in nanoscaled logic and memory devices. And people working memory have spent a lot of time and effort in optimizing devices to be in a binary 0 or 1 state. And then what happened is that we neuromorphic guys came, took the device and said, oh no, I want all states in between. Unfortunately, this introduces a lot of variability in the device. And in my study, I figured out how the variability interplays with circuit variability in Wernicke call circuits, which have many applications in competitive learning. And at the end, I demonstrate this framework, analytic framework, on a quantized fully connected layer from an MLP. And this is useful because if you want to validate accuracy of a network in hardware, you need to validate it for all the validation examples. And if you need to do this for devices and circuit variability, you need to do a lot of simulations. But with an analytic framework, you can assess this accuracy immediately. Hope to see you all at my poster.
Thank you, Jonas. Next up is Dennis Klinko.
Thanks. Hi. This poster is a spin-off of a more theoretical work about capacity, informational capacity in recurrent neural networks. And this particular poster is about echo-state networks which are based on hyperdimensional computing. So I guess many people know about echo-state networks, but not everybody knows about hyperdimensional computing. So hyperdimensional computing is basically ultimate example of an approach where you compute with noise. So everything is at first is a random numbers or random vectors, which is like you basically generate your concept based on noise. And then you have several different operations and you start to aggregate your knowledge using these operations on your noisy vectors. And the beauty of hyperdimensional computing for conventional hardware is that they can be binary. So you can operate on binary random vectors. While echo-state networks, they traditionally operate with floating point operations. And in that work, we basically made a hybrid. So we changed all the floating point operations in echo-state networks to this operations with integers in hyperdimensional computing. And as a result, we got an architecture where the reservoir states were they are integers. So we basically operate on integers in your reservoir, which of course saves you a lot of memory. So if you want to hear more details, you're welcome to pass by my poster. Thanks.
Thank you, Dennis. Next up is Eric Mueller.
Hi. So this is a twofold demonstration. So we also have some posters, but it's mostly a demonstration of the brain scale systems, the first and the next generation systems. Johannes will have a talk later this afternoon about the next generation system, which is shown on the left side here. We have prepared several small demos. One demo shows a stability experiment that uses STDP or modification of STDP to achieve activity stabilization over time. We have a small Pong player that learns using reward-based STDP, and which runs in real time, or accelerated time, so you can have a look at how fast the Pong game is running. And we also have some kind of characterization demonstration of the structured neurons, which are now available on the last next generation prototype. And yeah, and for the first generation system, we have prepared another demo.
Yeah, so what you see in the upper right plot is a teaser for my talk on Thursday, and to fully appreciate the results I will present, you can get an introduction to the BrainScale's wafer scale system that you can see below, and which you will also be able to play with via remote connection.
Thanks.
Thank you. Next up, we have Wilke Ollen-Abentorp.
Hi, I'm Wilke Ollen-Abentorp from the SUNY Polytechnic Institute. I work within the same collaborative research group as Gengo Trichakma. And currently we're developing and putting into production this fully integrated memoristive CMOS dynamic adaptive neural network array. And one of the ways that we program this is we have to discover the structure for the program that we want to run on the chip. And currently we do that through evolutionary optimization. And if you're familiar with EO et al., you'll know that the core of EO is making a bunch of guesses at the problem and then combining and crossing over and mutating these potential solutions until you find one that's correct for the problem that you want to solve. If you're thinking that this is a very expensive and kind of brute force way to do it, you're right. And part of the problem is that we really need to find better ways to do this and narrow down the pool of potential solutions to the problem. So the work that I'm presenting on is my approach to kind of narrowing down the potential number of improvements to a problem. So if you want to, say, introduce a new node into a solution to a problem or change a weight, this is a way of using dynamical systems theory to actually analyze that before you even have to evaluate fitness or the performance of the network and say, is this potential mutation actually going to make a change in the network, or is it going to be something that's actually the same? So if you want to hear about that, you can come see my poster. Thanks.
Next, we have Rutvik Vaila.
Hi, this is Rutvik from Boise State, Idaho. And then we have been working on classification problems using generic neural networks, spiking neural networks. And the first kind of network we tried is a convolutional neural network where the input was rank order coded MNIST data, and then the intermediate weights kind of look like parts of a digit. And we kind of modified the Python for neural networks, like the API, in order to be able to do the convolutional weight sharing. And the second kind of network we've been trying is a fully connected network, kind of inspired by Dr. Maas's work here. It's a k-winner take all, and the interim weights look like digits, and we hope to add some extra layers in order to be able to do classification. And once we will finish both networks, we're planning to transfer it to Spinnaker and then see the classification accuracy. And we are also looking forward to test this network on two kinds of encodings, that is rank order coding and as well as Poisson coding, and then see how it works. Part of the problem has been the neuron parameters and how do we set those parameters, and we really want to address those things. Thank you so much.
Thank you. And our last brief introduction is Eugene Watkins.
Hi, everyone. My name is Eugene Watkins from Los Alamos National Laboratory. Our poster is focused on comparing the standard JPEG image compression with 3 different neuromorphic image compression techniques. So we use CIFAR10 thumbnail images for training and testing in our work. CIFAR, if you're familiar with CIFAR10 thumbnail images, you know they're very low resolution images, which is considered much difficult to compress compared with the high resolution images because it contains much less redundancy. So here is one of the main results for the poster. The first column A is the input original uncompressed images, and from column B to column E are the image reconstruction result after 50% of compression from bottleneck autoencoder, JPEG, compressed sensing-based sparse coding with random, and regular sampling. Personally, visually, I think sparse coding contained the best reconstruction result. We used 3 different methods to evaluate the reconstruction result as pixel-wise matrices, classification matrices, and perceptual matrices as the difference between original and the reconstruction representation produced by deep neural network classifier to evaluate the quality of reconstruction for all those 4 image compression techniques. If you're interested in this work, please stop my poster. Thanks.
Thank you. So that should do it for our brief introductions. Why don't we give everyone a round of applause?